Alright, hello. We're going to be working through a organic synthesis reaction today, and so today we're going to be converting this simple alkyl halide into this complex benzene, like phenol with amide group with this alkyl group here, and so it's so complicated that I can't even really name it on the spot. So how do we convert this to this? It might seem very worrisome just looking at this problem, but we'll go through this step by step, and so it will become clear to you once we have gone through this. Alright, so let's just go through some retrosynthetic analysis here in order to solve this problem. Alright, so the first step, let's work backwards, right? We have an amide group here. And so typically before an amide group we have an amine group, and so and we typically add some kind of acyl chloride in order to convert an amine into an amide, right? So that means we know that the step before was an amine. All right, so like I said before, we probably added some kind of acyl chloride. So let's just write that. Let's call this step 9. Now, of course, we're assuming that we know that there's 9 steps here, so we already have 9 steps written out. Just for time's sake, don't want to take up too much time with this video, but as we said, we added acyl chloride. And when we add acyl chloride here, we end up with a very acidic product, and so we want to get rid of the acidity by adding a base such as sodium hydroxide with water, and that will basically ensure that instead of NH2 plus here, we're going to have just the hydrogen, and so that's going to be a neutral organic compound. Alright, so what's our next step here? We want to somehow get to this, right? So that's still a long way to go, but one other thing we can do is maybe convert this into a nitrile group, because it is typically the nitrile group that we convert into an amine with this carbon hanging out here, right? So that's kind of the main ways that we do that. So we know that we're going to end up with, we're going to begin with a nitrile group on this side. Okay, so with the nitrile group on this side, we know that to convert a nitrile into an amine, we have to reduce it by adding lithium aluminum hydride. Sorry, kind of got mingled up in here, but yeah, so that will convert this into an amine with the carbon hanging out on that side. So let's call that step 8. Alright, so let's continue working backwards. Working at a good pace here. So now this is typically added on by, some of the reactions that we learn is the diazonium substitution reactions, right? And so in order to do diazonium substitution, we have to first have some kind of amine group. And notice that this amine differs from this amine because this has an extra carbon while this amine does not. And so that allows us to carry out the diazonium reaction. And so the diazonium reaction looks like this. Right, the diazonium, and then we add copper cyanide so that the nitrile group can be added on there. Alright, so that is step 7. And then let's keep working back. We're getting closer. Alright, so this will be step 6. Okay, so before we have an amine here, we typically have a nitro group because it is the nitro group that we can actually add onto the benzene ring. Okay, and so the nitro group, this is and in order to convert the nitro group into the amine, we have to use hydrogen on palladium, right? Okay, and you might be wondering why there's this double bond here. Well, we won't really know that until we go through the previous steps, but what we do know for sure is that hydrogen over palladium reduces all double bonds other than, of course, this double bonds in a benzene ring into single bonds. And so we know that some kind of double bond was here before getting erased. Okay, so now let's continue working backwards to step 5. And so if we have a double bond here, then that means we probably went through elimination. But before we think about that, we have to think about how we added this nitro group here. Sorry, the top was kind of out of the way, but in order to add the nitro group to a benzene ring, that is through the combination of nitric acid and sulfuric acid. All right, and that will add the nitro group on. But we also know that will protonate an alcohol, right, to form this elimination. So we know that the compound beforehand had some kind of alcohol here. So let's right, and so it makes sense the alcohol is at this location because if you protonate this, the water will leave, the hydrogen will shift here, and then these open hydrogens, which are less sterically hindered, will be taken away, and then double bond will form. All right, so we're almost done here. How do we get from this alkyl halide into and somehow change it into a phenol group? Well, it's really not feasible within the context of our course to know how to somehow convert this into that directly, but we do know how to add carbon compounds to each other via Grignard reactions. And so in order for Grignard reactions to work, we probably start off with something with bromine in it. And then we can add the magnesium here to make it a Grignard reagent and react it with some kind of carbonyl compound with phenol in it, right? So the first step would be to add magnesium with ether. Second step would be to add the carbonyl or the aldehyde, right, with the phenol group. And now that's how we do it. We added the phenol group onto this alkyl halide. And finally, we had to add the acid in order to protonate the alkoxide to form an alcohol. All right, so that will be step 4. And if we go backwards here, this is still not the same as that, although we're pretty close, right? But in order to get from here, we probably went through some kind of Markovnikov addition. So that means that we started off with a alkene. And in order to get this alkene into this bromine, we added HBr, and it's going to add Markovnikov, and so it's going to add the hydrogen here, and then the bromine is going to go on the more substituted carbon. Okay, and so now we can kind of say, okay, well, how do we get from here to the bromine? So this we probably, if we look at it from a forward direction, we probably did some kind of elimination. However, the bromine is located on a primary carbon, so typically it's less likely that an elimination will occur and more likely that a substitution will occur. So, I mean, while we can go from here to here, another thing that we can do to make sure that we get better yield is to, start off with a alcohol. And so what that does is we can add a strong acid to this alcohol, the water will leave, and then we can actually eliminate that way. So then we add sulfuric acid to protonate that, the water leaves, and then the water will actually take away a hydrogen and produce elimination. So this would be considered E1 elimination. And finally, in order to go from here to here, this is just a simple substitution reaction. Again, it's on a primary carbon, so substitution is very likely to occur. So we can even add something like sodium hydroxide, and the hydroxyl group will come in and substitute for the bromine. All right, so sorry forgot to fill in the numbers here. 3, 2, and 1. Okay, so very quickly we were able to go through the reactions, work backwards, and with each backward reaction we were able to figure out what reagents to use in order to produce the previous or the next organic compound. All right, so just take a look at this. Sorry about that. All right, and just let it sink in. I know this is a lot, but with practice, you'll get these reactions down, and it will hopefully become a piece of cake with time. So hope you enjoyed the video, and I hope you learned a lot about organic synthesis reactions just from this one well, not simple, but complex reaction. And keep practicing, and you'll get it down. All right, thanks for watching.